happen is that I'll go through a few slides, and pretty quick we will go to the point where we need to make sure everybody is installed correctly on their laptop. So that's where we make a technical break and go from one to another and make sure everything works. And take coffee if needed, and then we'll continue. So we're working about programming the RC-64 in a very limited, restricted manner that can be done easily on our laptop. Before I go into it, I want to show the endpoint. So let me get online and make sure you get to see this. Yeah, you do. Okay. So we said there would be a competition at the end with a prize, and the goal of the competition, of course, would be to get to this level. I need a little bit of audio. So she is doing sorting. Her name is Maggie, and this is, you find it on YouTube, the Maggie sort algorithm. And of course she's there because she's doing a perfect job. With a trial and error. Now, can anybody guess why this is not a very good algorithm for our purpose? Lesson. Any idea?
She's testing all the possibilities.
Huh?
She's testing all the possibilities.
Yeah, she's looking at all the possibilities, but this is not a bad thing, right? But what's the wrong thing about it?
Cycle count.
Cycle count, yes. Yeah, good job. But she's a serial computer. She only does it in series. And the question is, how do we parallelize it, right? And that will be part of that. We will go to a more organized algorithm. Here's one of them. Let's see. First I need to run this at twice as fast, because you don't need to go through. And then I'd better go to the interesting part. So this is students in a high school in Australia demonstrating sorting algorithm, which I use in class when I teach algorithm. Merge sort. So you understand, they go in pairs and they get sorted. And then two pairs get merged because you merge previously sorted lists. So now they are merged. And now you take four people and two go to four, and you merge them. And now you merge the two eights. And every time you compare the first two in each list, and take the smaller one and put them in this. Okay, so this was merge sort. This is only one way of doing it. Hold on, let me start that. We don't need the other ones. Of course, everybody can download this demo. On the right-hand side is quick sort, which is always quick. On average, it's n log n, but it's better than that. Merge sort in the middle, which is where we are heading, and bubble sort extremely slow on the left. So we sort that. Quick sort is done, merge sort is merging, and bubble sort is bubbling. that's always like this. If you take a look slightly slower, so merge sort is always fast. And now you see how merge sort starts in small groups and just merges sorted list until you get the one. So that's where we're heading. And the goal will be, and as we go along, it will become clear why this is a challenge. This is a very simple thing to do in school, but this is a challenge for what we are doing. So it will take us an hour or two to understand why this is not straightforward at all on a machine and programming model that we are doing. So back to the slides. Okay. So this was the picture of the architecture that we looked at, and I kind of hidden a few things. So there's a hardware scheduler, there are 64 processors with their internals and shared memory. Everything else is removed from considerations now. We don't care about I/O, we don't care about accelerators, and we don't care about host control, monitor, and so on. And by the way, we don't care about this sub-bullet of, it's DSP with caches, and so on. There are more things that we don't care about. Here in the slide, it doesn't exist in the copy that you have, but I will email that later. So we have 3 levels of parallel programming. At the top level, there's multiple RC-64 chips with distributed computing and message testing or shared memory, but these are interesting issues for another day. And here in the middle is a single RC-64 chips with 64 cores and shared memory. And that's where we focus today. And in the bottom, it's everything that Ragai has just described with DSP and specific of VLIW and SIMD that we will not do today. So we just focus on the middle. And not only that, we don't really simulate everything, but we use what we call a MTE or many task emulator that you now have in this card. And on the left it shows the real model of the RC-64 or the MacSpace chip. On the right it's just a model, simplified model of the MTE. Scheduler, very simple processors and shared memory. That's it. By the way, we don't care about the network. Accessing shared memory happens by miracle. So we don't care about it. Here is a table comparing the real thing and the emulator. On the left is the real thing, and it has 64 processors. On the right, it says 1 through 64. You know what? Actually, I'll show we can go any number. So we can make believe we have up to 1,000 cores or so on. We can do more, but we don't care about them today. But we will care about programming for much larger number of cores, and we'll see why. Second line, it says parallel. Only 64 are parallel, but in the MTE it's emulated. We actually execute the role of one core after another in our serial program running on our laptop. On the left it's DSP, on the right we actually use the x86. I assume that all of your laptops have x86 inside or compatible. You have to be to buy your laptop in China in order to have anything other than x86 inside. They have MIPS processors. No, not AMD. In China you can buy a laptop with MIPS processor inside and Linux. Made by Lenovo, by the way. So on the left, we have the instruction cache, data cache, local memory. We don't have anything like this in the emulator. On the left, we have a hardware scheduler. Here we have an emulated hardware scheduler. It's managed by the same code, but the same behavior. Shared memory on the left, limited by 4 megabytes, unlimited memory, practically unlimited on the right-hand side. Of course, if you increase the problem size, eventually it will run so long and then crash. I'll show an example of how you run mode. On the left there is input output. On the right, just forget about it. We do either file read write or just printf. And today we'll only use printf. Accelerators on the left there is none, and host control and monitor there is none here. So how does it work? It has a special way of running things that's shown in this slide. We construct a temporal picture. Here's a task graph that says first execute A, and then in parallel or concurrent, you can run B and C. Remember yesterday we talked about concurrency. Concurrency means that they can run together, but I can also run them in any order sequentially. And of course, on the emulator, where we only have a single processor, physical, we run A first and then B next and then C next, issued by the scheduler according to these dependencies. And whenever we run a task, we record its running time, TA, TB, and TC. Later on, we can make believe, and the emulator gives us a log, output log, of this make-believe temporal picture that that A ran from this time unit, and then B and C were running in parallel, and B completed maybe here, and C completed there. And this is the start, and this is the end. And we get a very nice picture, although we know it didn't really happen that way. In the real chip execution, it would be probably something like this. Not guaranteed, of course, because the scheduler can do whatever it needs to do. Maybe there were 100 other tasks running in parallel, and scheduling will be different, but at least these dependencies are fulfilled. There is no violation. Just to remind what concurrency is, so we define this term parallel processor where we have many cores, and they may execute simultaneously. Simultaneously mean at the same time. So simultaneous tasks execute at the same time on many cores, but concurrent tasks may execute simultaneously, or may execute sequentially, or may execute in any order. And obviously they must be independent, otherwise they wouldn't have been concurrent. So on task we define three types of tests: regular, sequential, and single instance. I don't know if the word regular is the best choice of the name, but we are used to that name, so let's say they are regular. The other one could be irregular, but that's not a good idea. So regular. And it may return a return code, 1 or 0, which is true or false. It's a token, and it is sent to the scheduler. And the scheduler may observe it or ignore it, as we'll show. Duplicable tasks each of them is sequential, but there are many concurrent instances. So multiple instances, each one sequential, and they are all concurrent. Can run in any order. And they do not return any return value, because otherwise it would have been a mess. The quota is how many of those? It is maybe set or changed by the program or set in a task graph. And a task graph is usually a file with the suffix .map. So the file type is .map. File specify the task graph. The name could be anything but .map in our system. When you try opening it by default on a Windows machine, it will usually open some other tools that expect a .map, so be careful. And there is each instance receives its own instance number, and it's available to the code, as we will see. The third type is a dummy task. It does not incur any code. It doesn't really happen. It does not get allocated to a processor. It's only done, used inside the scheduler just for what we say token algebra, combine tokens and create new conditions inside the scheduler. We sometimes use them, we'll just skim over. There are other tasks here in light gray because they are not used in the MTE. High priority tasks, I described them yesterday when we talked about input-output. So there are the interrupts and handling input-output and so on. That's beyond us, we don't need that. We are only focusing on actual algorithms that ignore that. Here are some graphics. If you want to draw task graph in graphics or understand what it is, then we'll look at this picture. So here in the, on the left here, we have 3 different types of tasks that require a completion on only at least one of the incoming errors. So it's an OR causality. So if only one token came in, if only one of the preceding tasks completed, this one can execute. And the OR function is marked by this circle. And this is regular, duplicable is always marked by a double block, a shaded block, and dummy is done. By the way, the regular can come out with return code, return true or false, and there could be something else that depends on true. One thing can depend on true, something else can depend on false, or yet another thing can depend on I don't care. But only one of those is used. Only either the two on the left or one on the right. And on the right hand side, it's the end relationship. All preceding tasks should be finished before this specific task can be allocated. Just this and this and this and this all must be finished before I can go on. And you can create complex structures, usually with dummies. So here on the left, either of those two must be finished before I get a token here. Sorry, on the right hand side, either of these two must be finished before I get a token, and so on. So, but we don't need these today. Today we will use very simple cases of O, very simple O, and very simple AND. That's it. The text in a file, the text in a file to describe the task map or task graph is very simple. And the one thing that exists in the text that does not show in the picture is that order determines priority. We'll talk about that when we get there. So here is how we start the work. So everybody needs to set up their MTE by forget about the first line, unless we run into a problem, we go back there. And the first thing you want to do is install the Oracle virtual machine virtual box from this address. And so this will take a few minutes if you haven't done that. And it will offer you to download the extension, and we want to download the extension. So either you click on yes, let's download the extension as you do the install, or you go to this bullet and it tells you how to do this. So after you install the virtual box, you open the virtual box manager, VBM, go to File, Preferences, Extension, so on, so forth. And after everything works, we may need to disable the display 3D acceleration. Usually we ignore that on most modern laptops. If somebody comes up with a very old laptop, we may need to do this. David, sometimes MacSpace has a tendency of giving people very old laptops, so you may be the victim here. But everybody else will get the virtual machine. It's on the disk, on this card that everybody has been given, and we go on from there. So now we stop for 5 or 10 minutes, and we'll just walk from one to another. I'm leaving this on and make sure everybody has installed the virtual machine and can video resume. Good, thank you. What we expected to be printed, and when we say just printf, it prints on the console. And I can have many things print to the console, and if they are concurrent, I don't know what order they will be printed, but that's fine. At least in this case it's easy, because remember, the concurrent execution is never simultaneous. And the emulator executes each task, each instance after another, in whatever order. So all the printfs come fine. We will start having printf issues if we have the hardware and suddenly so many concurrencies try to do printf, then we have to do something else. But let's not worry about this today. We don't have the hardware anyway. So we got all of them working. Now we want to look at, take a closer look at the files. So the problem with this kind of Eclipse system on a virtual machine or whatever is that don't believe the names of these files here after you execute. I need to again go to the name of the project, right click and say refresh. It says F5, but I don't believe F5. I click refresh. And it changes to make sure all these files, all these names really point to the updated files. And then the first thing I want to look at is rc64.log. Double click, opens it up in this window right there. Let's enlarge it and take a look at the log. By the way, the log is very low, right? It will be really low. So we want to just take a look and see what's in it, but we never read it again. We only go there if something goes wrong. But the log really records each and every step of the emulator, starting every instance, finishing every instance, and so on. The first line says RC log, simulation debug level is set to 1. Nice, we can get the log recorded. The second one says simulating 2 cores. In this case, the RAM was not 64 core, it was running in my machine on 2 cores. In your machine, if you open up log.64, most likely you will get on this second line, it will say simulating 64 cores, because 64 is the default. And the last time I ran this, I set the number of cores to 2. I'll show you later how. But I forgot to set it back to 64. It doesn't matter. So I assume that all of you will have 64. Cycles per clock ratio is 1, doesn't matter. DDR size is, well, 4 megabyte, but we don't use, or 4 gigabyte, we don't use DDR now. Utilization is saved in rcutilization.csv. We will later look at this file. This will be our most important output file that we will use the rest of the day. But it will always be there. Now some other messages, and then it says it allocates regular tasks, RC scheduler, config tasks, code 0, code 1, whatever. This is just setting up everything. The actual execution starts here, in this line. You see, allocating regular task A to core 0. And, by the way, quickly after that, task terminated. Task ID is A, start time was, you see, just some random number that's the same as the number on the left on the allocate statement. So 1443341.